Welcome back, everybody. Section 7.2, day 1. Hypothesis testing for the mean, sigma known. So basically, if I tell you that section 7.2 is hypothesis testing for the mean where sigma is known, what do you think section 7.3 is?
It's not known.
And it's not known, right? Exactly. So we're going to do 2 sets of hypothesis testing, when the mean is known and when the mean is unknown. Where did I put my section 7.3 notes? Hold please.
Is it up here? I think it has to be up here.
Put them up there. Nah, I think it's in that vanilla folder right there. Section 7.2. It's 2 days.
Nah, it's terrible.
All right. Now, we are going to do hypothesis testing in 2 different ways. Okay, we're going to do hypothesis testing in 2 different ways. 2 different ways that we can state our outcomes. Honestly, the outcome should be the same no matter what. Whether we reject the null or fail to reject the null is not going to change based on how we do the problem. But there are 2 different methods. The first one is deciding what we do based on our p-value. Okay? Decision rule based on p-value. We're going to do a decision rule based on p-value and then a decision rule based on rejection region. So this is the first method. Decision rule based on p-value. To use a p-value to make a conclusion in a hypothesis test, we compare the p-value with alpha. Remember, alpha was our level of significance. Okay? And that can change depending upon the context of the problem. We're going to do alpha based on the 0.1 level, alpha based on the 0.01 level, alpha based on the 0.05 level. Okay? And the smaller you make your alpha, the stronger your decision becomes. The bigger you make your alpha, the weaker your decision becomes. So what we're going to be doing is we're going to be calculating a p-value based on the statistics, based on the numbers, based on our sample. And then we're going to make a decision about the parameter. Right? We're going to stick with mu, but you could do this for sigma as well. We're going to stick with mean, but again, you could do this with sigma. So we're going to compare the p-value with alpha. And that p-value again comes from the sample. We'll talk about how we get that p-value soon. Okay, so here's where we make our decisions. If our p-value is less than or equal to alpha, then we reject the null. If our p-value is less than or equal to alpha, then we reject. And remember, rejecting the null is kind of like our goal, right? Your goal is to reject the null. And you have to, in your claim, whatever angle you're taking toward this thing, you have to put your claim strategically into the null or alternative hypothesis. Because remember, if I'm trying to disprove a claim, I'm going to put it in the null. If I'm trying to disprove a claim, I'm going to put it in the null because I hope to reject the null and I hope to disprove that claim. So if I can make the statement, I reject the null hypothesis, I have disproved that statement. If I want to support a claim, I put the claim in the alternative. So therefore, if my statement is, if I can make the statement to reject the null hypothesis, that is a roundabout way of accepting the alternative. We never actually state that, but that is a roundabout way of supporting the claim. Then if it's the other case, if p is greater than alpha, then we fail to reject. So that's really what we're looking for. If p is less than or equal to alpha, then we can reject the null. If p is less than or equal to alpha, then we can reject the null. If it's not, then we fail. We fail to reject the null. So for example, the p-value for a hypothesis test is 0.0359. Yeah, and that will come from the table. It's a 4-digit decimal. That'll come from our z-score table. And we'll talk about how we compute that pretty soon. So the p-value for a hypothesis test is 0.0359. What is your decision based on the level of significance? Okay, if the level of significance is at the 0.05 level, do we reject the claim? Well, is 0.0359 less than 0.05? Is that a true statement? Yes. 0.0359, my p-value is less than alpha, so therefore we reject the null. We reject the null if p is less than alpha. Okay, so what if my alpha is 0.1? Okay, 0.0359. Is that less than 0.1? Yeah. Yeah. We reject it again. But can I reject it at the 0.01 level? No, because 0.0359 is not less than 0.1. I know I could say greater than, but I like to put a slab, I like to keep it as less than, because that keeps it straight in our minds. So if I know that 0.0359, oh sorry, that's a 0.01. Since it's not less than 0.01, I can say, well then I have to fail. I have to fail to reject. Not guilty. Not innocent, but just not guilty. Questions about that? So it's all based on how our p-value compares to alpha. And again, we're getting that p-value from our statistics, from running the numbers. Okay. So how do we find that p-value? After determining the hypothesis test, standardized test statistic, and the test statistics corresponding area, you do one of the following to find the p-value. For a left-tailed test, the p-value is the area in the left tail. Okay, think about it this way. For a left-tailed test, that p-value is the area in that tail. For a right-tailed test, it's the area in the right tail. For a two-tailed test, see, right tail, left tail, very straightforward. For a two-tailed test, you just gotta keep your mind on the fact that, okay, in that area, excuse me, the p-value is 2 times the area in the tail of the test statistic. That's your p-value. It's got a 2-to-1 relationship to alpha. Okay, it's got a 2-to-1 relationship to alpha because in terms of the alpha, if my level of significance is a 0.01, then that 0.01 has to be split up into between those two tails. So each tail has a 0.05. So therefore, when I'm choosing to do something with my p-value, I have to double my p-value to compare it to alpha. In the other way, in the choosing the rejection region, I kind of work it the opposite way. I take alpha, divide by 2, and then I compare it to my test statistic. But again, we'll probably get to that tomorrow. But right-tailed and left-tailed tests are pretty straightforward. Now, the weird part is going to come in the right-tailed test because thinking back to our z-scores, when we think about area in the tables, the area underneath the curve on your z-score chart is always left side, right? It's always left tail. So you just have to, take a 1 minus to complement if it's a right tail. Okay, so let's start with our easiest part, the left tail. Let's start with our easiest one, the left tail test. Find the p-value for a left tail test with a test statistic of negative 2.28 and decide whether to reject the null if the level of significance is alpha is 0.1, 0.05, then 0.01. Okay, so if our z-score is negative 2.28, if our z-score is negative 2.28, I'm going to go to my table. I'm going to go to my z-score table, and I'm going to find negative 2.28. Now I go negative 2.28, and I see 0.0113. 0.0113. Okay? And that comes straight out of my table, the z-score table. Negative 2.28 is 0.0113. Now, what I'm going to do now is compare. Okay, so if alpha is 0.1, so my p-value for the left tail, actually, yeah, no, that's right. my p-value for the left tail is 0.113. So at the 0.1 level, when alpha is 0.1, okay, my p-value is 0.0113. Is that less than 0.1? Is that a true statement?
Yes.
Yeah, 0.01 is less than 0.1. So therefore, I can reject the null. Okay, so if the alpha, if the level of significance, drops, and I don't want to say drops, because you might be thinking, oh, it's a weaker statement. This is actually a stronger statement, right? 0.0113. Is that still true? Oh, sorry. Why did I make it 0.1? I meant to say 0.05. Excuse me.
Yes.
Is that still true?
Yes.
Yes. So we're still rejecting the null at this point. Yeah. Yeah. The smaller you make your alpha, the stronger the statement is. Okay. Alpha being 0.01. Can we reject the null anymore? No. We fail to reject. Yikes. Sorry for the poor handwriting. I fail to reject the null. Okay. And that, as I go along, is a stronger and stronger and stronger statement. Okay. Rejecting the null at the 0.05 level is a stronger statement than rejecting the null at the 0.1 level. Okay. All right, so that's a left tail test. Now, think about it this way. If I want a right tail test, okay, so to find the p-value for a right tail test statistic of z.1, 1.81, I'm going to go to my table. Make that a little arrow. I'm going to go to my table and look for 1.81. So z-score table 1.81, 0.9649. 0.9649. Now, am I really going to be comparing 0.9649 with 0.1, 0.05, 0.01? No, I got to do the complement, right? Because this is the area under the curve to the left of z is equal to 0.181, right? This is technically this area. Yeah, so always remember, if it's a right-tailed test, you have to take 1 minus 0.9649 because that will truly get you the area underneath the curve to the right. All right, so let's do that. 1 minus 0.9649, and that is going to get me 0.0351. Yeah. Wait a second. Why do I not have that? I have 0.881. 1.819649. What did I use? 0.8810. What the what? Oh, I did the wrong number. What the what? 1.18. Oh, yikes. 0.8810. Excuse me. 0.8810. Got the wrong number off the table. 0.8810. Ooh, yikes. I think I was looking at 1.28 or something. I don't know. 1.18. Never mind. That's much better. Okay, so 1 minus 0.8810 gives me 0.1190. Okay, and that's the p-value. So for a right-tailed test, or turn it into a decimal, and then take 1 minus. All right, so let's decide what we want to do. If alpha is 0.1, 0.1190, is that a true statement? No, so I'm failing to reject. Now, think about this. If I have failed to reject at the 0.1 level, what's going to happen at the 0.05 level and 0.01 level? I'm going to fail to reject in all of those as well. Because is this number going to get any smaller? No. So 0.1190 is going to be, these are not going to be true for 0.05 or 0.01. Does that make sense? So if you try to make it a stronger statement, I'm still going to have to fail to reject, right? And my goal is to reject the null, right? My goal is to reject the null because that's the more definitive statement. All right, so that's left tail, right tail. Let's talk about two-tailed then. This is when it starts to get a little murky, when the water starts to get a little bit more cloudy. Find the p-value for a two-tailed test with a test statistic of 1.78 and decide whether to reject the null if the level of significance is alpha 0.1, alpha 0.05, and then alpha 0.01. So we're keeping the alphas the same. We're just changing up the test statistic. Now it's 1.78. Okay, let's try to get the correct number here. 1.78.9625. I guess I should check it for 9625. So we have z is equal to 1.78 gets us to 0.9625. Okay, now think about this. That is giving me the area under the curve of all of this, right? What do I really want? I want area under the curve of here and here. Okay? So what I need to do is I need to take 1 minus. 1 minus is going to get me 0.0375. And then double it, right? And that will give me my true p-value. Oh, p-value is equal to, p-value is equal to 2 times 0.0375. 2 times 0.0375, which gets me 0.075. And that's the p-value that I'm going to be using. So let's make our statements based off that. So if alpha is 0.1, so is 0.075 less than 0.1? Is that a true statement? Yeah. So I can reject the null at this level. Okay, at the 0.05 level, can I still reject it? Oops, sorry, 0.075. And we could say, no longer a true statement, right? That is not true. So therefore, this is when we have to start failing to reject. And if I fail to reject it at the 0.05 level, what's going to happen at the 0.01 level? I have to fail to reject as well, right? So here, 0.01 level, same thing. Does that make sense? And it's got that 2-to-1 relationship. Can't forget about that 2-to-1 relationship. That's where sometimes a lot of people go haywire on that. Okay. So, is it time? Is it time to actually do it? Oh, we got to talk about z-score first. Now, remind ourselves about z-score, right? We have already done this part. We already know this came from a previous chapter, right? Right. Ready or your pass?
No, I'm good.
This came from a previous chapter, z-test for mean of mu. This is coming out actually from chapter 6. The z-test for a mean is a statistical test for population mean. The sample is random, population is normal, or n is at least 30. This is from chapter 6. X minus mu over sigma divided by the square root of n. This is when sigma is known, right? This is when sigma is known, because those were the two sections out of chapter 6. When sigma was known and when sigma was unknown. This is when sigma is known. When population standard deviation is known, when sigma is known, and we're trying to make a decision about the population mean, about mu, I use this calculation. X bar minus mu divided by sigma divided by square root of n. And that mu is coming from our statement, our claim, right? That mu is coming from our claim. We're going to take X bar, we're going to take our sample statistic, our sample mean, we're going to subtract away mu, and we're going to divide it by sigma divided by the square root of n. not n minus 1, n. All right. So just as a reminder, now this is the same thing that we were talking about before, the steps for hypothesis testing. We state the claim in math and verbally. Write it out. Identify the null and alternative hypotheses. Figure out where our claim is and where it goes in. Second thing, specify the level of significance. Specify the level of significance. Third thing, determine the standardized test statistic. Figure out whether you want to use Z or T. It's going to be Z. The sigma's known. Next thing, calculate that Z. Find the area that corresponds to Z. Go to your Z-score table. Next thing, figure out what your p-value is then. What we did before. Figure out what your p-value is. Is it left-tailed? Is it right-tailed? Get your p-value accordingly. Sixth thing, make a decision to reject or fail to reject the null hypothesis. Make your decision based on your p-value and your level of significance. If p-value is less than alpha, then you can reject. If p-value is not less than alpha, then you fail to reject. And then the last thing is interpret your decision. Interpret your decision. Right? Make sure you always put that into words. Like if I show you the Chapter 7 assessment, there's just a big blank open space for you to perform all these things. Okay? The expectation, I'm not going to outline every single step for you. I'm not going to say, oh, show me the level of significance, then show me the test statistic, then show me the p-value. Think of it like a proof, right? Think of it like a proof. Think of it like I need to show all of these things to support my answer, to support my decision whether I'm going to fail to reject or reject the claim. Okay? That's really how you've got to think about these things. Like when I go to grade it, I'm going to be looking for every single part of this. Like, and I'll be putting check marks by each piece. I'll be looking for, okay, where's your claim? State your claim. Show me the null and alternative. Check, check. State your level of significance. Check. Show me your Z value. Show me your Z score. Check. Get the correct Z score. That's like one of the only mathematical things about this. Like that's the only computational thing about this. Step 3. What's your Z score? X bar minus mu over sigma divided by square root of n. Next, it's all decision making. Okay. Find the area that corresponds to Z. Go to your table. Done. Check. Found the area. Next step. Find the p-value. Are you just going to use that exact same value, or do you got to use 1 minus, or you got to do 1 minus times 2, whatever it may be, left tail, right tail. Next step. Okay, make your decision. I want to see the statement fail to reject or reject. Then the very last thing you should have at the very bottom is at least one sentence, 1 or 2 sentences interpreting your decision. And it's always got to be based on the claim. Don't just finish with reject or fail to reject. Don't do that, because that's not really telling me anything, right? You defined what your null and alternative hypotheses were based on the claim, right? You've got to then say, okay, interpret your decision, interpret your reject or not reject in context of the claim. Okay, let's do it. First hypothesis test. In an advertisement, an oil change company claims that their average customer getting an oil change waits for less than 25 minutes. That's their claim. We're Valvoline. We are saying that we make customers wait for less than 25 minutes. A random selection of 42 customers has a sample mean of 23.1 minutes. And we know that the population standard deviation is 4.6 minutes. It's interesting. Like, I don't know. In my mind, how do we know sigma? How do we know population sigma? Like that seems weird to me that we know population sigma. Whatever. Tomorrow, or not tomorrow, but section 7.3 seems more real life to me. The fact that we will not know sigma and that we have to use S. Okay, but we do know sigma here. It's 4.6 minutes. Is there enough evidence, enough information, enough evidence to support the claim that the alpha 0.01 level and then the alpha 0.05 level? Okay. And we're going to use p-values for this. Honestly, I should have asked those in the opposite direction there. I should have asked first about the 0.05 level. Because if we fail to reject it at the 0.05 level, we're going to fail to reject it at the 0.01 level, right? Because the 0.01 level is a stronger statement than the 0.05 level. But, all right. So first thing I want to do is state my claim. What is my claim?
Less than 25 minutes.
Mu is less than 25 minutes. Okay. So that's my claim, right? Null or alternative? Ooh, be careful.
No, stop.
The alternative, right?
Not equal.
Right?
Mhm.
The null is the equality. And here is my claim. Which makes sense because, if I am Valvoline and I want to support my claim, right? If I want to support my claim, where should the claim go? The alternative hypothesis. If my claim ended up in the null, the only thing I could do was disprove myself. I don't want to do that. Okay, so we have stated the claim. Mathematically, we didn't do it verbally, but we kind of talked through it. Identify the null and alternative hypotheses. Good. Next step is going to be specify the level of significance. Okay, so let's talk about it at the point. We'll do the first one here, the 0.01 level. Alpha 0.01. Next thing, determine the standardized test statistic. All right, so that means we're going to do our z-score. Let's figure out our z-score. Let's also define everything else that we know. I like to make myself like a list of everything that I know. Mu is going to be 25. A random selection of 42 customers, that's n, has a sample mean of 23.1, x bar. And we know that the population standard deviation, sigma, is 4.6. Okay, I have everything that I need to have for my z-score, right? X bar minus mu divided by sigma divided by square root of n. X bar minus mu divided by sigma over square root of n. Okay, let's calculate that. Okay, X bar is 23.1. You might be saying, oh, well, if my population, if my sample was 23.1 and I want to show that it's less than 25, isn't that enough? Right? Isn't that enough? But the thing here is that my sample is 23.1, but my sigma is 4.6, right? So is it far enough below to kind of negate my standard deviation, right? That's what we're really looking at here. X bar minus mu divided by sigma divided by the square root of 42. Now, why can I even use this? I didn't say that anything was normally distributed, but my sample is bigger than 30, right? So that's why I can even use these formulas. 23.1 minus 25 divided by, we got 4.6 divided by radical 42. Negative 2.6, we're on to the nearest hundred, negative 2.68. So that's my z-score. Let's change that z-score into a p-value. Okay. So negative 2.68, oops, that's not a time. Negative 2.68 will turn into what? Be a little cheater here. 0.0037. And we get that from the table. If you go to your yellow table, you look up negative 2.68. You know what? I better just check myself because I screwed up once already today. Negative 2.68. I only get one mess up per classroom. Negative 2.68. 0.0037. Okay, good. All right. So there, now, is this a left-tailed, right-tailed, or two-tailed? Where does that come from? Where do we look for that? The alternative, right? Okay, so because this is a less than, that tells me that this is a left-tailed, right? And the reason we need to know that is because at this point, we want to find the area that corresponds to z. Actually, we found the area that corresponds to z. Now we want to find the p-value, and that is determined by whether it's a left-tailed or right-tailed or two-tailed test. If this is a left-tailed test, what do I have to do with that 0.0037? Nothing. So my p-value, 0.0037. Now, next step, make a decision to reject or fail to reject based on that p-value. So I then say, okay, is 0.0037, is that less than 0.01? Is that less than my alpha? Yeah. That is, yes, that is a true statement. So I can say, reject the null. Okay. Now, is it still less than 0.05?
Yep.
Yeah, because if it's less than 0.01, it's got to be less than 0.05. That's still right. So I'm going to reject the null for both of these levels of significance. Right? To finish it off at the end, I need to create my statement. I need to put it into context of the claim. So if I reject the null, what do I say? I can support the claim. Right? I reject the null hypothesis, therefore supporting the claim. There is enough evidence to support the claim. To support the claim that the average wait time is less than 25 minutes at both the 0.01 and 0.05 levels of significance. That make sense? Remember, the difference between rejecting the null and failing to reject the null is rejecting the null makes that definitive statement, right? I can support the claim. I can reject the claim, right? I can support the claim or I can disprove the claim. If I fail to reject the null, remember that you can't support or disprove anything. All you're saying is there's not enough evidence to support or there's not enough evidence to disprove. That's like saying there's not enough evidence to convict, right? Not guilty. Not necessarily innocent, but just not guilty. All right, we'll pick up here tomorrow. Sound good? Yep. Deal.